Welcome to Lecture 60, our final lecture. We've been through a lot together. You know a lot of physics at this point. You should be proud of yourself. You can do calculations, you understand phenomena, you understand technology, you understand the theoretical basis behind a lot of what goes on in physical reality. And we physicists should be proud, too, at how much we've been able to understand the universe around us. But in this lecture, I'm going to take us in a different direction, because I'm going to give us a humbling surprise. And the surprise is this: we don't understand most of physical reality. This is a point I've kind of danced around briefly in the previous lecture, but now we're going to face it full on. We simply don't understand what most of the universe is made of. In particular, there is dark matter. And we have very little idea what dark matter is. And if that isn't bad enough, even dark matter doesn't take us to most of the universe. There is also dark energy, about which we know even less. And so I'm going to end on a humbling note and leave you with how much more physics has to do if we're really going to understand our universe. So let's begin with dark matter. Dark matter is an idea that's been around for a while. It was first proposed in 1933 in connection with galaxy motions. Evidence for dark matter has been building. What we do know about dark matter, partly from our understandings of the formation of nuclei in the Big Bang that I described in the previous lecture, we know that the dark matter cannot be made of baryons. It cannot be made of the stuff, the neutrons and protons, the quarks, that ordinary matter is made of. So it's something new and something different. And several more or less routine possibilities like neutrinos and several other things that we know about have been pretty much ruled out. Let's look a little bit deeper at dark matter. First of all, what we know about dark matter is it doesn't interact electromagnetically. Therefore, it doesn't emit electromagnetic waves. That's why it's dark. It's not luminous. It's not part of the visible stuff that we see in the universe. Furthermore, because it doesn't interact with electromagnetic waves, it's transparent to light and other electromagnetic waves, so we can't detect it by its blocking of electromagnetic waves, even if it weren't luminous. So it's dark in both these senses. It has no electromagnetic interactions. We know that it doesn't interact via the strong force either, the force that binds quarks to make nucleons and nucleons to make nuclei. And that means we can't detect dark matter with interactions involving either electromagnetism or the strong force. It has very limited interactions, if it interacts at all, with atomic nuclei. It does interact gravitationally. It is, after all, matter. And matter has mass, and mass is the source of gravity. So dark matter does interact gravitationally, and that's pretty much how we know about it, and that's pretty much all we know about it. It may be that dark matter also interacts via the weak force. Maybe, maybe not. It depends on what the particles are that comprise dark matter, and we simply don't know. But if it did interact via the weak force, we would have indirect means of detection. The prime candidates for dark matter are particles called WIMPs, weakly interacting massive particles. And they go beyond the standard model. They're not something that's predicted by the standard model of particles and fields that we talked about back in Lecture 58. There have been no confirmed detections of dark matter. However, there are quite a number of different dark matter searches going on around the world, and there have been some tantalizing hints that haven't risen yet to the level of statistical certainty. So it may well be that by the time you're watching these lectures, or maybe a year or so beyond, that we will have a firm confirmation of a dark matter particle, and that will open the door to our understanding what dark matter really is. How do we know that dark matter exists? Well, we've had evidence of various sorts. First of all, when we observe galaxies get together in clusters of galaxies. When we observe galaxies moving around in clusters, their motions are not consistent gravitationally with the amount of visible matter we see and with the amount of invisible dust that we can infer is in these clusters, and so on. We look at galaxy rotation curves. How do the stars move around the galaxies? And here's a graph of a typical galaxy rotation curve. On the horizontal axis, I'm plotting distance from the galactic center. On the vertical axis, I'm plotting the velocities of stars. And what you would expect is a curve something like this. Near the galactic center, there's not a lot of mass interior to where you are. Velocities tend to be small. As you move outward, the mass interior to where a given star is increases, and the rotation velocity is the orbital velocity of the stars around the galactic center increase. But as you get toward the outskirts of the galaxy where the matter gets more diffuse, you expect a fall-off in the velocity curve. That is not what you see. What you see is that fall-off doesn't happen. It's as though there is invisible matter, lots more of it, in the outer reaches of the galaxy that we don't see. That's evidence for dark matter. There's also dwarf galaxies in clusters. We see these very dense clusters of galaxies in which collisions are tearing the larger galaxies apart, and the dwarf galaxies seem to be surviving as though they were protected by a cushion of invisible matter that's keeping them from getting damaged in the raucousness of this cluster of galaxies. Gravitational lensing, this bending of light that Einstein first predicted with general relativity, also gives us evidence of unseen matter that is affecting the trajectories of light from distant objects. Galaxy collisions, which we can look at with gravitational lensing, are an example. And the picture down here is a very famous picture. It's often said to be the first direct evidence for dark matter, although it isn't quite direct evidence for dark matter. But what you're seeing here is the result of a collision of two galaxies, and the blue regions are shown by gravitational lensing, and so they are, in effect, imaging regions where there's a lot of matter that may not be visible. And so it looks like what's happened is these galaxies have gone through each other, and the dark matter has interacted in the collision gravitationally, and we're seeing the dark matter sort of affected by that collision. Massive clusters of galaxies provide us another example through gravitational lensing. The cosmic microwave background that we discussed in the previous lecture also provides us with evidence because the CMB anisotropies, anisotropic means varies with position in the sky, anisotropies that we analyzed are consistent with a flat universe, and I'll say more now about what a flat universe means. In a flat universe, the density is such that the kinetic energy of the matter in the universe is just barely enough to overcome the gravitational attraction of all that matter, and that universe can just barely have enough energy to expand forever. It's sort of a cosmological analog of escape velocity, where a ball, if I throw it with just the right speed, about 11 miles a second from the surface, 11 kilometers a second from the surface of the Earth, will have just enough energy to escape to infinity. That's the analog, a classical analog of the critical density. And what we find in the universe is that the visible matter, the matter that we can see, is far below what is needed to make up the critical density. So this critical density is a really crucial number, and understanding how the actual density of the universe compares with the critical density is crucial to understanding its fate and the nature of the universe. And in fact, what these cosmic microwave background observations are telling us is that the density of the universe is essentially the critical density. Since this quantity is so important, let's do a quick calculation and figure out what it is. So here we are at our big monitor, and let's calculate the critical density of the universe. We'll estimate the critical density, and we're going to assume Newtonian physics, which isn't a bad assumption given that we're talking about a flat universe where the general relativistic curvature is not significant. The critical density is the density for which the total energy of a galaxy is zero. Just like escape speed is the speed for which an object leaving the surface of the Earth has zero energy and gets to infinitely far away with no kinetic energy and no potential energy, but starting out it has kinetic energy and negative potential energy, and they sum to zero. We know what the kinetic energy is. It's a half mv squared. We know that potential energy in the case of gravity is minus big G, mass of the gravitating object, mass m of the object we're talking about that has this energy, divided by the distance between the two. Here little m is the mass of the galaxy in question. Big M is the mass inside some sphere of some radius r. And I'm doing that because you'll remember that a spherically symmetric distribution of mass acts as if it was a point source of mass at its center. So I can think of a galaxy, a distance r, on the edge of a sphere of radius r, as being influenced by the mass within that sphere as if it were located a distance r away at its center. That's why I'm doing that. So m is that big mass, and little m is the mass of the galaxy. We'll see soon that neither of them matters. The Hubble relation tells us that the velocity of that galaxy is h naught, the Hubble constant, times that radius. So I'm going to stick that velocity into the kinetic energy. So on the left I have a half mv squared, now written with v squared being h naught r all squared. Subtract the gravitational potential energy, the sum to zero. Well, pull the gravitational potential energy to the right side of the equation. Here's my equation. The little mass m cancels. It doesn't matter what the mass of the galaxy is. No surprise there. We found that back in Newtonian mechanics whenever we dealt with gravity. Work a little bit on that equation. I've got h naught squared. Pull the g down to the other side. Pull the r squared underneath with this r, and I get an r cubed. So there's my equation. Now, I'm going to divide that equation by 4/3 pi. You'll see why in just a moment. On the left, the 4 and the pi make that 2 into an 8 pi. The 3 goes upstairs because I'm dividing by that 4/3 pi. On the other side, I'm just going to write it as 4/3 pi downstairs, and that's multiplying r cubed. And the reason I wrote it that way is that 4/3 pi r cubed is the volume of a sphere. And so this is the mass inside that sphere of radius r divided by the volume, and so that is the density. And because I started with the assumption that the total energy of the galaxy was 0, that's the critical density. Let's figure out what it is. In lecture 59, we found that the inverse of the Hubble constant in seconds was 4.3 times 10 to the 17 seconds. We got to that on the way to our calculation that the universe was about 14 billion years old. Let's do the numbers. Rho critical is 3 Hubble constants squared over 8 pi g, the Newtonian gravitational constant. The 10 to the minus 2 up there is taking h naught to the minus h. This is 1 over h naught. We're taking 1 over h naught to the minus 2 power. That'll give us h naught squared. There's the gravitational constant, the 8 pi. Work it out. It's 10 to the minus 26 kilograms per cubic meter. Now, that may sound like a very small density, and it is. But it's the average density of the entire universe, including the vast spaces between the galaxies, the spaces in our solar system that are basically vacuum. All that is included in there. So it's not surprising that this is a small number. What's interesting is that this number, although it's small, is far too big to be explained by the presence of ordinary visible matter. So let's look a little bit more at this critical density. We can actually sum up the fate of the universe with one number. That number depends on the density of the universe, and it expresses the density in terms of the critical density. If the density is low compared to the critical density, we've got really weak gravity, kinetic energy dominates, and the universe will expand forever. In general relativity, that corresponds to a universe whose overall curvature is kind of the 4-dimensional analog of a saddle, negative curvature we call it. If there's a high density relative to the critical density, we've got strong gravity, the potential energy dominates, the expansion will halt, the universe will eventually collapse, and in general relativity, that corresponds to positive curvature, some kind of 4-dimensional analog of a closed sphere. That, by the way, is how we can have a finite universe that had no boundary. If we're right at the critical density, we have 0 total energy, and in general relativity, that corresponds to a universe whose overall structure is flat, even though it may be curved very highly near things like black holes, more weakly during things like the sun, near things like the sun, but basically, overall, the universe is flat. So we now know that the universe is, in fact, close to the critical density. We want to now calculate, or we want to look at what that means for the fate of the universe. And this is all summed up with a single parameter. It's given the letter capital Greek omega. And omega is simply the ratio of the actual density of the universe to the critical density of the universe. And we know from these studies of the cosmic microwave background that we in fact seem to live in a flat universe where omega is 1. So the value of omega summarizes the entire fate of the universe. In one number, we've wrapped up the universe. Omega equals 1, and we are quite sure from observations, and this has only been known with any certainty since about the year 2000, that omega is essentially 1. So the density is the critical density, because omega is the ratio of the density to the critical density. Now, here's what observations tell us. Remember, the visible matter that we can see has much lower density. In fact, it has a density that's less than about 5% of the critical density. And what that means is that the ordinary visible matter can make up at most about 5% of the stuff that there is in the universe. We need lots more stuff to make up the other 95%. The visible matter simply won't do it. Visible matter, the hot glowing stars, the clouds of gas that occupy galaxies, the planets in our solar system, our own sun, us, add that all up and you get only 5% of the critical density. So the conclusion is there has to be some dark stuff that is not visible matter, and it has to be that the density parameter for the universe, this omega, which we know from observations is equal to 1, is a sum of 2 omegas. One is the omega due to visible matter, and one is the omega due to dark stuff. And the omega due to visible matter is about 0.05, and the omega due to dark stuff has got to be about 0.95. And so that is why this lecture is so humbling, because most of the universe, about 95% of it, is stuff we don't understand. And we're going to spend the rest of this lecture looking at that stuff. The extra monkey wrench in all this is the new thing we discovered around 1998, which is cosmic acceleration. Because according to general relativity, no matter, whether it's visible or dark, can explain cosmic acceleration. Because what matter does is to attract itself, according to Newtonian gravitation, to curve space-time according to Einsteinian gravitation. And either way, the effect is basically as if there were an attractive force between matter. What cosmic acceleration that began 5 billion years ago requires is some kind of repulsive gravity. How could that possibly be? We need this anti-gravity. We need some kind of repulsive interaction. How do we fit that within our theories of gravity? It requires a new form of invisible, not matter, matter won't do it, but a new form of invisible energy, and that's called dark energy. So now we've got dark matter, and we've also got dark energy, and the CMB anisotropies tell us something else. They tell us that dark matter isn't enough to do it. Dark energy is the dominant mass energy in the universe. In this era of accelerated expansion, at least, dark energy dominates. There was an earlier epoch in the universe, before about 5 billion years ago, which quite coincidentally, and with no relation to this, is about when the Earth formed. There was a time earlier when matter dominated. Dark matter, probably, but matter. Now dark energy dominates. It's the dominant mass energy in the universe, and we know this again from those cosmic microwave background observations. So now we have to write that the density parameter, omega, which we believe observationally to be 1, consists of omega of matter, and I'm lumping dark matter and regular matter into that omega of matter, plus omega of dark energy, and that omega of dark energy is most of it. We'll see just how much in a moment. How would this dark energy work? Here's Einstein's gravitational equations from lecture 49. Equations, because remember, it's 10 of them. And again, we didn't do much with this equation, but again, what it says is that space-time geometry depends on the presence of mass and energy, and if you have mass and energy, you get this attractive force between masses, the force we call gravity. Well, it's not really a force in general relativity, but let me talk in Newtonian terms to make it easy. However, as I pointed out at that time but didn't write explicitly, the mass energy includes pressure. Now, pressure normally is sort of a form of internal energy, and it would simply add to the mass energy and add to this attractiveness. But there's a special kind of energy associated with the vacuum. There must be energy in the vacuum. This is equivalent to this fudge term that Einstein had added to the equation, and that I'm not showing here. It's required by the uncertainty principle because it requires sort of random fluctuations. We can't know that the vacuum has zero energy. It has to have a minimum energy called the 0-point energy. And it exerts a negative pressure. And that gives rise to a repulsion in Einstein's gravitational equations. If that mass energy T term on the right, which includes pressure, got negative, then gravity would become repulsive. And that's the kind of thing we think has happened. And we can either handle it thinking about it this way or sticking this extra cosmological term in Einstein's equations. We aren't actually sure what the dark energy is, so we don't know exactly how it fits into the equations. It actually looks pretty close to the term Einstein came up with in 1917, but we aren't sure yet. But how would you get a negative pressure? What does a negative pressure mean? Let me give you an analogy that helps us to understand this. Here from lecture 25 is a piston cylinder system we talked about a lot. There's an ordinary gas in it. It obeys the ideal gas law. Pressure times volume is the number of molecules times that Boltzmann constant times the temperature. Now suppose that gas does work on that piston, letting it rise up, increasing its gravitational potential energy. And this is an insulated cylinder, so no heat can flow in, so there's no new source of energy. Where did the energy come from that lifted the piston? It came at the expense of the internal energy of the gas. So the internal energy of the gas went down as the gas did work and expanded. That's all we need to remember from lecture 25 for this purpose. And that's an ordinary gas, and an ordinary gas most certainly exerts what we would call positive pressure. It's pushing up on that piston. Now let's look instead at a cylinder system containing a vacuum. Now remember, the vacuum is not quite empty. It's got this energy density, and the energy density of the vacuum turns out probably, we're not sure of this, but probably to be constant. It doesn't change. And so what happens is, if the vacuum does work on that piston, in other words, if the vacuum expands, if there gets to be more vacuum, the energy density stays the same, but there's now more volume, and so there's actually more energy. And so the energy does not go down with expansion, but rather goes up. And by the analogy in this picture, That's the opposite of what happens with an ordinary gas with positive pressure. And that is the origin of the negative pressure and the repulsive effect of this mysterious dark energy. Even though we don't understand it fully and know what it is, we do know that it has a negative pressure and that therefore it causes gravity to become repulsive. And in eras in the universe when dark energy dominates, the repulsion is the main thing that's going on. And that's why we're getting the accelerated expansion of the universe today. Well, let's wrap up by looking at some of our constraints on understanding the composition of the universe, and then I'll give you just a few hints about where physics is likely to go in the future from here. Here's a diagram in which I'm plotting on the bottom axis omega sub m, omega of matter. And on the vertical axis, I'm plotting omega of dark energy. Remember, those two have to add up to 1 because we are quite sure we live in a universe where the total omega, the ratio of density to the critical density, is 1. So omega is 1. It's the omega of matter plus the omega of the dark energy. And I'm going to show you constraints from 3 different observations. Here's the first one. This blue graph coming in from the right are observations of the cosmic microwave background. The cosmic microwave background constrain the values of omega of matter and omega of dark energy to lie somewhere in that long rod-like thing, most probably near the center of it where the color is a little bit lighter. But that's all we can say from the cosmic microwave background alone. It could be that we've got a lot of matter and a little bit of dark energy. Could be the opposite. We don't know from that one alone. Next, we've got supernovas, observations of distant supernovas, which were the first things that gave us a hint of cosmic acceleration. They're that green data now coming in from the upper right. They constrain the values of omega matter and omega dark energy to be somewhere in that green area, which intersects the cosmic microwave background. Finally, there are observations of galaxy clusters, which provide a different set of constraints on these 2 numbers, and they're in this yellow to red colored area. And somewhere there is a statistical best fit where all 3 of those intersect, and in fact, the best fit from the data we have today is that the universe consists of 28% matter and 72% dark energy. Omega matter is about 0.28, omega dark energy is about 0.72. That's the humbling thought I introduced at the beginning of this lecture. We don't know what most of the universe is made of. And let's just look at that in a simpler pie graph. Matter is about 28% of the universe. Ordinary matter is less than 5%. So that 28% is therefore about 23% or a little more dark matter, which we don't understand. Dark energy is 72%. We know even less about dark energy than we do about dark matter, except that it does exert this negative pressure. So if I were to present a kind of pie graph, here's what the universe looks like. The stuff we understand is the ordinary matter. The dark matter we know a tiny bit about. We're beginning to observe it with gravitational lensing, but we haven't yet, at least as I'm recording, detected a dark matter particle. And if we want to be even more humbling, let's take a look at this graph just in terms of 2 quantities, the stuff we understand and the stuff we don't understand. The stuff we don't understand is 95% of the stuff that makes up the universe. The stuff we do understand is only 5%. Wow, what a humbling thought. Now, I could stop there, but I won't, because there are other things we don't understand. And I want to just end this lecture and end this course by giving you a hint of what those are. We don't know how gravity fits in with the other forces. In fact, in general relativity, it's not even a force. Gravity in general relativity is the geometry of space-time. It's continuous. And yet, there must be some tiny, tiny scale size. It's called the Planck scale, about 10 to the minus 35 meters, at which quantum effects have to become important even for gravity. And we simply don't understand how to reconcile those theories. We don't understand yet how to reconcile the electroweak, the merging of electricity, magnetism, and the weak force, and the strong force that holds quarks together. We're close to that one, but we don't have it yet. We understand that that can be done consistently with quantization. We just haven't done it. One possible solution to all these quandaries is something you've heard about, and I'm going to address in only a moment and not say much more about, and that is string theory. String theory is an idea that the fundamental entities of nature are not particles, but they're sort of one-dimensional string-like things. They have extent in one dimension. Some of them are closed back on themselves, and they can vibrate. And the vibrational modes of these strings correspond to the individual particles. There are great enthusiasts of string theory out there in the physics community. There are physicists whose whole careers involve studying string theory, one of whose consequences, by the way, is that we live in a universe of multiple dimensions, maybe 10, maybe 11, depends on which theory you're talking about, but many more dimensions than the 4 dimensions of space-time that we know about. And some of those other dimensions are so-called compactified. They're wrapped up into tiny little loops and we don't see them, but they may still have some effects on physics. I'm not sure about string theory, and I'm not going to spend a lot of time on it because string theory, at least at present, seems to present no ways to test itself experimentally or observationally. And string theory is not one theory, but many, many, many theories. And if there's many, many, many theories, how do we figure out which one is right? So I'm not going to say a lot more about string theory, but it is something you will hear more about in physics, and it may someday give us the breakthroughs we need, in particular to show how gravity fits in with quantum physics. What else don't we understand? Well, we don't know what there was before the Big Bang. We don't even know if that's a meaningful question. But maybe it is. Maybe it isn't, because maybe the Big Bang began time itself. We just don't know. Do we live in a multiverse? Is our universe just one of many? Well, I thought the universe was everything there is. Well, maybe. But maybe there can be other universes that aren't even connected to ours, that can't even be connected to ours causally. Here's a fanciful artist's conception of all these different universes kind of floating around in a void, but that's a misleading picture because there's no void for them to float around in. Others may even have different physics. Only a few of those universes may happen to have the right physics and the right conditions for life to have evolved and for physicists to have evolved and for consciousness to have evolved to contemplate those universes. New universes may form when a region of space-time gets kind of pinched off, as in the formation of a black hole. And here is a wonderful picture from a book by J. Richard Gott called Time Travel in Einstein's Universe, which I'd recommend to you. And this shows a so-called time loop at the bottom where time goes around and around and around like it did in that movie Groundhog Day, if you saw that. And then time starts evolving. And those trumpet-like or bugle-like structures show the evolution of different universes in time. Those universes are expanding because they're getting wider as they go out. And new universes have budded off, and this one shows 4 universes that originally started as one and are now evolving separately and completely unrelated causally. Is this possible? Who knows? Physicists would argue that Einstein's general relativity contains at least the seeds of the possibility of this kind of creation of new universes and time loops and all kinds of strange things. Alan Guth, who came up with the idea of the inflationary universe, says the universe is the ultimate free lunch, because if you calculate how much energy it takes to bud off one of these new universes, it takes exactly 0 energy. Some kinetic energy, some negative potential energy, and the thing grows off on its own. So there's a lot more we don't understand. Will we ever get to a theory of everything? Now, I'm not going to end this lecture with a challenge, but I will give you a challenge right now. Here's my challenge. Come up with a theory of everything. If you can do that, you've got the holy grail of physics. We aren't going to have that theory until we understand the nature of dark matter and dark energy. We aren't going to have that theory until we've reconciled general relativity and quantum physics. We aren't going to have that theory, I believe, until we at least have a feel for how these emergent properties arise, and I don't know if we're ever going to have a theory of everything that will let us understand the more complex emergent properties, particularly consciousness. Well, there's plenty of physics left to do. We're going to be kept busy for a long, long time. There's a lot we don't understand, and let me end with John Archibald Wheeler's famous cartoon again of the universe that wonderfully evolved consciousness, and consciousness is looking back and observing that whole evolution of the universe, and that's what this course has been. Thanks for coming along. I've enjoyed it. I hope you have.